VLSos here. This is a video lesson on solutions on a graph. I'm not going to use a graph immediately. I'm going to take a look at this equation. The square root of 2x plus 3 is equal to x. I'm going to use the algebraic process to solve for x. I can see that I've got x in two places, but the first thing I'm going to do is I'm going to square both sides in order to clear this square root. I'm going to take the step of squaring both sides. When I do, the square root and the square will cancel out, leaving 2x plus 3 on the left. Now on the right, I have x squared. This is quadratic. I could put it in standard form and use the quadratic formula to find the solutions. I'm going to subtract x squared from both sides. I can see that I have coefficients of -1, 2, and 3. Using the quadratic formula, x will be equal to -b plus and minus the square root of b squared, or 4, minus 4 times the value of a, which is 1, and I'm going to account for the fact that it's negative by changing the sign out front to positive, times c, all over 2a. Continuing with the quadratic formula, I'm going to simplify the radical. 4 times 1 times 3 is 12. Add 4 to get 16. The square root of 16 is 4. So x is equal to -2 plus and minus 4 all over -2. Continuing, -2 plus 4 is a positive 2. Positive 2 divided by -2 is going to be -1. Second solution, -2 minus 4 is -6. -6 divided by -2 is a positive 3. This process gave me two solutions for x. But there's only one. How would I know? Let's analyze the graph. Going back to the original function, I'm going to use a graph to visualize solutions as intersections. If we consider the original function to be two different functions equal to one another, then I can graph these separate functions, in this case I've labeled it f and g, and look to the intersections of f and g. Where this expression crosses this expression, I will find a location as a solution to the equation. Let's see that happen. X is easy to graph. It is parent line. We'll call this the g function. The f function, or the square root of 2x plus 3, is a little more sophisticated. We could use graphing software, or we could use a t-table of points. It is a square root function that has been modified. It's been vertically dilated, and it has been horizontally translated left. The result will look like this, approximately. If we take a look at the graph, we can see that the equation graphed as two distinct functions, the left and the right, intersect at one location. The location is the point where x is equal to 3. This x value is the location of an intersection and therefore is a solution. And we knew that because we found it in the process. But if we're expected to find a second solution, we should expect to see a second intersection on the graph of these two sides. And we don't. At -1, we do not have an intersection. This right here is the 0, or the x-intercept of f, but it does not intersect with g anywhere around here. Let's test -1 as a solution to the original equation. If I put -1 in to the square root of 2x plus 3, I get 2 times -1 is -2. -2 plus 3 is +1. and the square root of positive 1 is positive 1. Positive 1 is not going to be equal to negative 1. So I've justified that negative 1 is not a solution. But it came from a correct process. There is no mistakes made here. In the process of solving for x, I got negative 1 as a solution without mistake. But I used a graph to confirm I should only get one solution. So what do we call negative 1? It's not a mistake, it's an extraneous solution. Extraneous is like extra. It's an extra solution that came out of the process, but it doesn't make the equation true. So extraneous solutions are not final answers. It's a little bit annoying that algebra includes the fact that you can get extraneous solutions. It's important if you go through a process to check your answers to see if any of them are extraneous. But doing so is tedious. It's better to understand what kind of processes can make extraneous solutions possibly arise, and then check in those circumstances. The hint in this problem that there may be an extraneous solution is the fact that you are undoing a square root with a square. Why would that create an extraneous solution? Because squaring cancels out negatives. And so you cancel out a negative with the square on the right side, but on the left, you're never going to cancel out a negative because it's still not ever possible to get a negative number out of a square root. So the process of squaring doesn't recognize that in this case, what you're squaring is not possible to be negative. So by the end of the process, you need to remember that originally a negative could never be under the radical. So if the process results in that, you should check it to make sure it's not extraneous.